Hello, welcome back. Today let's try to solve another Leetcode problem 354, Russell ever loops. So this is a very famous problem. Basically, for the Russell, we can put a one inside another one, but this is just for ever loops. So for the ever loop, each of them, it has a width and height. So how can we put it inside? It must be the width. So for example, the width should be strictly less than this one. So for example, 5 is strictly less than 6, but this 4 equal to 4. It means it cannot put it inside. Yeah, but for this one, 2, 3 can put it inside 5, 4 because 2 is less than 5, 3 is less than 4, it can put it inside. And let's check this example. 2, 3, 5, 4, and 6, 7. It means the length is 3. Now, let me first go to the whiteboard to explain my solution. After that, I'll go to the code editor to finish the coding. Actually, this is a very popular template problem. Yeah, and after you solving this problem, you can solve a lot of hard problems for the longest increase in subsequence problems. Now let's go to the whiteboard. First, let me explain it. Yeah, I will use this example 5, 4, 6, 4, and 6, 7, and 2, 3. Normally for us, our idea maybe we can use greedy. Why not? We just sort the array. After sorting, it will be something like 2, 3, 5, 4, 6, 4. Here I will keep it 6, 4, this one. Yeah, 6, 4, and 6, 7. After sorting, maybe you think I will check the longest increasing subsequence of the index 1 because I sorted according to index 0. But you will find 3, 4, 7, it is 3, it's the longest, but actually it's not totally right. So what if this 6, 4 changes to 6, 5? Let's see what happens. So here, this 6, 4 gonna be 6, 5. So what is the longest increase in subsequence? It's 3, 4, 5, and 7. Because after sorting, we're gonna think, oh, the start point with the index 0 has already been sorted. I just need to check the second index. So 3, 4, 5, 7, the longest is 4. But actually, the longest is only 3. Yeah, so this means the greedy didn't work. Yeah, actually, it works. It didn't work for the second index. Yeah, so this means if we sort the second index, index 1, in decreasing order, we can get the right result. This is similar to sweeping line problem. For the sweeping line problem, we also have the ever loop for example, this first add point here and the second start point here for the event. We have to deal with the duplicate overlap areas. Yeah, and this is similar for the Russell ever loops problems. So we still sort it, but we're gonna sort it for the first index in increasing order, for the second index in decreasing order. So it will be something like 2, 3, 5, 4, 6, 7, because first index is the same, but the second index will be in decreasing order. It will be 7 and 5. Let's see what happens. So we have 3, 4, 7. It's the longest 3. 3, 4, 5. It's the longest 3. It means only in this way we can get the right result. Yeah, you may wonder why not. What if we have another one? Maybe it's the same 6 and 7. It's exactly the same as the previous one. If we have a 6 and 7, it doesn't matter. So here will be another 6 and 7. Yeah, but for our result, we are taking strictly increasing for this 3, 4, 7, and 5. It is still 3. It didn't have any influence. Yeah, because after sorting the first index, we don't care about if there are so many duplicates. Because for the second index, we sorted in decrease order, so we will never have duplicate anymore after this way. Yeah, so this is the first method we need to think. So this is basically the problem solving skills. Now we are going to the second step. So that is our basic knowledge of the longest LIS problem, longest increasing subsequence problem. We should know at least there are two different time complexities for longest increasing subsequence. So for one, it is O(n) square. For another one, it is this is n square. For another one, it is n log n time. Yeah, for this problem, because the length is 10 to the power of 5, so we have to use n log n. Yeah, so for n square, it is very clear. We solved many problems of longest increasing subsequence, we used O(n) square. But for this one, actually, we have to use n log n time. How should we use n log n time? So we have to have the knowledge of how to solve it. So this knowledge is called patient sort. What do I mean by patient sort? It's normally for the longest increasing problem, it is O(n) square. But some guy, find a better way for solving such problem. Actually, it is n log n time. Yeah. So actually, the idea is very easier, but very hard to think about it. Yeah. So the idea is like playing with card. So we have an array. For example, I prepared it like 3, 8, 6, 5, 7, 4. Let's check first of all what is the longest. It is 3 maybe. 3, 6, 7. Yeah, the longest may be 3. I don't know. Let's find another number. Maybe we have a longest. Yeah, I think it is 3, 6 or 3, 5, 7. So the longest is 3. We just need to use our method to check. Yeah, why it can be 3 and why we can use n log n can make it to 3. Yeah. So for this method, basically we are checking the piles, how many piles of them. So we think of these numbers as a card. We're gonna separate this card into piles. We just check how many piles. So if there are 3 piles, so we're gonna return a 3. So for the piles, we will check the numbers one by one. So for the first number, if there's nothing for our pile, we just put a 3. Next, we're gonna prepare a 8. If this 8 is more than 3, we're gonna put this 8 to the second pile. And then we're gonna put the 6. When we are put the 6, we are going to check one by one. 6 is more than 3, but 6 is less than 8. So we're gonna put 6 just below this 3. Yeah. Now we are not going to put it here because we are always to find the smallest value, biggest value less than the 6. So 3 is less than 6. We're gonna put it here. Yeah. Next we're gonna put this 5. So 5 is less than 6. Yeah, and 5 is less than 8. So we're gonna, let me check if I did it right or wrong. So we always put, let me check this 6. Yeah, if this number is bigger than 3, we're gonna put it here, put it in the second pile, and then we find a 6. If this is smaller, we can, because 6 is bigger than 3, but 6 is smaller than 8, we're gonna always put a value smaller than this value, than the first value we find. Yeah, the 8 is bigger than 6, we're gonna put 6 under here. If it is bigger, we're gonna put another pile. So next for the 5, where can we put the 5? 5 is bigger than 3, we cannot put it here, but 5 is smaller than this 6, so 5 can put it here. Next, we're gonna check 7. 7 is bigger than 3, 7 is bigger than 5. Now 7 can put it here because 7 is more than that. Why? Because if this number 7 is more than this 5 and this 3, it means our longest subsequence can be increased. So this is why the greedy method. Now we are going to put the last one, 4. 4 is bigger than 3, but 4, I think I did something wrong. 4 is smaller. Yeah, I think I did it right. So 4 is smaller than 5. 4 is bigger than 3, but 4 is smaller than 5. We're going to put the first place at 5. We cannot put it below the 7 because we always use the greedy method. Yeah, and this 4 will be put it here because we always want to find more piles. Yeah, we will put it at the previous, yeah, as much as we can to the previous piles. We're gonna not put it here. So 4 will put it here. So how many piles? 1, 2, 3. And also for the piles, basically we can find a find a root. Maybe the root maybe 3, 6, and 7. So 3, 6, and 7. It is okay. Maybe 3, 5, and 7. Yeah, it is still okay. So actually this is 3. You can see that 3, 6, 7, and 3, 5, and 7. Only those two roots. So we only need to return the length of the pile. So it is 3. We just need to return this 3. Yeah, as you can, this method we're gonna check one by one. But this array, the piles array, is already sorted. So this is why we can use the binary search to insert it inside. And for the length of the longest increasing subsequence, maybe it is n. And for binary search, we insert it into the longest increasing subsequence array. It is log n. So that is why it is n log n time. Yeah. If you understand this, maybe you will, yeah, you can solve it easily because this is the hard part. So this is the problem solving skills. So this is your background knowledge. If you know this kind of knowledge, you can solve it. If you don't know it, you cannot solve it. So yeah, because this is sorted, this is why you can use binary search. Actually, the array, this is array. So inside the array, actually, finally, it's going to be 3, 4, and 7. Why? Because all these numbers will be covered. 8 will be covered by 6. 5 will be covered by 5 will cover 6, and 4 will cover 5. So finally, it will be 3, 4, and 7. We just need to return the length of the array. If we want to find a root, so this is one of the root, but not all of them. Yeah. Now let's go to the code editor to finish the coding, if you understand that. So actually, the coding should be much simpler for this problem, but the thinking is much harder. You need to think about a lot of the situations. First of all, about the sort. So the error loops dot sort. Yeah, in Python you can use the lambda function to sort it for the first index as increasing, second index as decreasing. So k equal to lambda, and you need to take one item. This is x. You take the item 5 and 4, and for this item you're going to do some lambda calculations. For the first one, it's going to be x0. It means for the first index it's going to be increasing, and second index it's going to be minus x1. So this means for the second index it's going to be decreasing. You just need a minus x. After that, I need to prepare a longest increasing subsequence array. From the beginning it is empty. Now I just need to loop through the error loops because it has already been sorted. So for with height in error loops, first of all, I'm going to check the index. So for the index is bisect left. I'm going to use the built-in library because this is much easier to understand. Because the core of the problem is not about using the binary search here. The core of the problem is to use the patient sort. So this sort, we call it patient sort. You can search that. There are some papers talking about this patient sort. That is O n log n time for the longest increasing subsequence problem. And here for the bisect left, you need to use the longest increasing subsequence and the height because you don't need to use the weight anymore. Now just need to check the index. If this index equal to the length of longest increasing subsequence, it means we can append it after the array. So we need to append the height. Otherwise, we just need to insert it. So for the insert, actually, it is the updating of the previous value. So LIS I should equal to 8. Finally, we just need to return the length of the longest increasing subsequence array. So this means a pile. Before there's the empty. Now you're gonna to put your card into the piles. Finally, you need to return the length of the piles. And here, the bisect left from the beginning, if it is empty, it's gonna be 0. So it means if I equal to 0, this length is 0. You're gonna to append the first one inside. You know, this code is much simpler than other applications, like when you are using a stack or something else. You can see that the template code is much simpler. So there are only like 7 lines of code actually solve the problem. Actually, this should not be counted because that is so simpler. Yeah, for the core code, basically there are 6 lines of code, and then you can solve it so easily. Now let me just run it to check if it really works. As you can see, it works. Now let me submit it to check if it can pass all the testing cases. Yeah, as you can see, it can pass all the testing cases because this is just a on log n time. Yeah, and this n is 10 to the power of 5. Thank you for watching, and by the way, you should understand this template. And for the similar problems, there are a lot. You can directly use it for solving many Leetcode hard problems. Thank you for watching. See you next time.